Welcome back. I hope you're fully refueled and refreshed and ready to learn about some types of 3D printing. In this part of the lecture, we will look at powder bed printing and fused filament printing. Powder bed printing was actually the first type of 3D printer developed, and it is really a modification of inkjet printing. It combines an inkjet printhead with an apparatus that can dispense powders. A schematic of a powder bed printer is shown on the screen in front of you. Rather than containing ink, the printhead contains a solution of binder. To make an object, a layer of powder is spread out on the build plate by a roller and the printhead passes overhead, spraying binder to adhere the powder particles together, forming one layer. The piston on the left rises to dispense more powder, which is spread out by the roller, while the build plate on top of the piston to the right is lowered. This process then repeats multiple times to build up the object. At the end, the object is removed from the build plate and any loose powder is shaken off. One limitation of this type of printer is that it cannot print hollow objects because the loose powder will be trapped inside. But it is the only type of 3D printing that is currently used to make a commercial product. That product, shown on the screen, is called Sprytam. It's a product made by a US company, Aprecia, was licensed by the FDA in 2015 and launched onto the US market in 2016. The tablet really contains just drug powder particles weakly bound together with the binder solution. The advantages of this are very good. There are no excipients, so that reduces cost and limits compatibility issues. The dose of the drug can be high. You can see that the product is available in 4 dose strengths up to 1 gram. 1 gram! That is a huge dose for a tablet. And finally, because the powder particles are only weakly held together, the tablet disperses very quickly when added to water. Aprecia has released a video showing how fast Sprytam disperses compared with a conventional melter tablet. So let's take a look. The product is therefore marketed as an oro-dispersible tablet. Often the cost of manufacturing with 3D printing is very high compared with conventional powder compaction. So to make a business case there must be a clear advantage of using the new technology. In this case, Sprytam is both high dose and oro-dispersing, and this type of formulation would be very difficult to manufacture with powder compaction. The other interesting thing about this product is how Aprecia uses the printers commercially. You might imagine there to be a factory full of printers, each individually producing tablets. But in reality, they change the production process so that printing steps occur in sequence on a conveyor belt. But rather than me explain, Aprecia also has a handy video that explains the process, which we can watch instead.
Let's take a look at the 3D printing process. First, a powdered medicine is spread into a thin layer. Then, a liquid is dropped onto the powder to selectively bind the particles together into a thin, porous layer. This process is repeated a specific number of times to add more layers based on the dosage, building the product from bottom to top. The result is a porous drug product that disintegrates with just a sip of liquid. Learn more at Aprecia.com.
Although it's used commercially, powder bed printing is expensive, so most research labs use cheaper technologies. The most common type of 3D printer, and you may have seen one in our labs or have one at home, is fused filament printing. In a fused filament 3D printer, the feedstock material is an extruded polymer, much like a thin piece of string. You can buy them on spools in a range of colours and made of various polymers. The filament is fed into the printhead and melted, turning it into a viscous liquid. This liquid is then extruded through a small nozzle onto a build plate. The build plate is often kept cold, so when the liquid polymer touches it, it turns back to a solid. The nozzle moves across the build plate in an XY raster pattern, building up the first layer of the object. Once the first layer is finished, the build plate moves down and the process repeats for the second layer. In this way, the object is created layer by layer. This was the first type of printer that we bought for our own labs, partly because it was cheap and partly because the fact it uses extruded polymers is a big advantage pharmaceutically. For one thing, the filaments are made with hot melt extrusion, which is a standard technique used in the pharma industry for making drug polymer blends. Thus, hot melt extrusion is ideal for making drug-loaded filaments. Secondly, because it is used in the pharma industry, it is easy to set it up to operate under good manufacturing practice principles, which is required to make products for human use. And finally, and this is something that we focus on in our own research, it is possible to extrude pharmaceutical grade polymers, known as generally regarded as safe or GRAS. It's really key to print with GRAS polymers if the tablets are to be used in humans, as the commercially available polymer filaments are usually made of ABS, PLA or PVA, and these are not good for human use. ABS is what Lego bricks are made of, for instance. We use fused filament printing for making pharmaceutical tablets, which we term printlets. Our first paper was published in 2014, and you can see examples of the printlets we made on the screen in front of you. We realised very quickly that the dose of the printlets could be varied through the printer software. A CAD file really describes only the surface of an object, and you need to tell the printer how thick to print it. Also, if you don't tell the printer to fill the void space inside the object with polymer, you will end up with a hollow object. The amount of polymer that is printed in the void space is called the infill percentage. You can see that as we increase the infill percentage, the printlets become increasingly more dense. This allows us to vary the dose of each tablet without changing the outer dimensions, and is one of the main ways in which 3D printing lends itself to personalised medicine. Each printlet can be fabricated in around a minute. If you're wondering how the filaments actually come together once printed, the SEM images on the screen show you a cross-section of a printlet. You can see the individual strands that were extruded from the printhead and that they are fused together after printing, which is why the tablets are so strong. Now, you might say to me, that's great, Simon, but what use is a tablet made of polymer? And that would be a fair question. In fact, we asked ourselves that too. Handily, the US Food and Drug Administration recently introduced the requirement for a new type of product that is ideal for this type of printing. The US, and indeed most of Europe, is currently experiencing record numbers of patients addicted to opioid painkillers. I'm sure you're aware, but prescribing a patient more than a week or so's worth of opioid medication is highly likely to start a dependency on the medication. Once dependent, a patient will seek to take higher and higher daily doses of the opioid, and it's incredibly hard to wean them off it. Dependent patients will also try to alter opioid medication to get the dose absorbed faster, often by crushing the tablet or dissolving it in alcohol. To try and prevent this, the FDA mandated that any company wishing to launch an opioid medication in the US must also offer an abuse-deterrent formulation. Abuse-deterrent medications, as the name suggests, are designed to resist being crushed or dissolved in alcohol. Now, what sort of tablet might resist crushing? That's right, a polymer-based tablet. We had a go at making printlets with abuse-deterrent characteristics, and you can see the results on the screen. I have also put a link to the paper so you can read the results for yourself. The tablets were mechanically very strong and resisted crushing, and also didn't change their release profile in the presence of alcohol. Another benefit of 3D printing that we realised early on is that you can make tablets with geometries that would be really difficult to create with powder compaction. Because the mathematics of the shapes are known, it is possible to calculate their properties, such as surface and volume. We chose the 5 shapes shown on the screen: cube, pyramid, disc, sphere and torus, and fabricated sets of tablets with either constant surface area to volume ratio, or constant mass. All the printlets were drug loaded, so we could conduct dissolution tests to see which geometric factor was most important in controlling the release kinetics. And what did we find? The answer is not what we were expecting. I expected that constant surface area to volume ratio would be the dominant factor, but in reality there was no correlation, as you can see on the screen. There are a lot of data, but just focus on the purple line which represents the pyramid. You can see it was the fastest releasing shape when the surface area was constant, but the slowest when the surface area to volume ratio was kept constant. We think the reason we didn't see similar release profiles for all shapes was because once added to water the printlets swirled and dissolved. So although their geometric features were the same initially, they soon changed during the test. The data also show, again, that you can control the release kinetics from printed tablets very easily by changing shape. Interestingly, or not, this paper is currently the most highly cited of all our 3D printing papers, 445 citations when I last looked, which I think is because it contains pretty pictures. I said earlier, it's key to be able to print with GRAS polymers, and the development of printable filaments from GRAS polymers has been a key element of our research. Is it easy? Absolutely not. You can extrude a filament that looks and feels great, bendy and pliable, but it won't print. Or you can have a filament that snaps like spaghetti and it prints fine. Recently, we have been applying machine learning to our data to see if we can get some idea of the likely printability of filaments. We predicted the likely printability of over 900 formulations using this method, and the reference is given on the slide if you want to check that out. The pictures on the screen show 3 filaments printed from varying grades of HPMC, low, medium and high molecular weight, and the corresponding printlets. When we conducted dissolution tests on the HPMC printlets, you can see that the lower the molecular weight grade of the polymer, the faster the release kinetics. Again, this shows a mechanism by which the dissolution behaviour of printed tablets can be controlled. When someone asks us what dissolution profiles we can make with 3D printing, we show them the following graph, because we can, in fact, make any dissolution profile, from immediate release to sustained release, by varying the type of polymer. Right, time for another break for refreshment. When we come back, we will look at how we can use 3D printing to make polypills. See you in a bit.